Let's look at this problem out of the angular momentum section out of the Hibbeler book. So this says when the 2 kilogram bob is given a horizontal speed of 1.5 meters per second, it begins to rotate about the horizontal circular path at A. So that's this bottom circle that we see here. And it says if the force F on the cord is increased, the bob rises and then rotates about the horizontal circular path B. We want to find the speed of the bob around path B, and then we also want to find the work done by the force. So basically, we're going to pull this cord this way, which causes the little mass to rise up, and then eventually it's going to stop and it's going to, circle around in this horizontal path. Again, notice it says it's a horizontal path, so there's no elevation change or anything right here. So the height stays the same once it's on path B. Now we want to find a velocity, and then we want to find work done by the force F, which is essentially the tension that's going to be applied to that little cable. So this, like I said, is out of the angular momentum section. So let's kind of look at that first, and then we'll see if that's enough to find what we need. All right, so if we remember our angular momentum equation, we've got basically the integral of the sum of the moments about our reference point, and notice that's a vector, and that's going to be equal to the change in angular momentum about that same reference point. Now, first thing I want to do is I want to see if I can get rid of this side here. So this is that angular impulse, right? So if I can get rid of this, if this is not here, if it's equal to 0, then I have conservation of angular momentum, which makes the problem a little bit easier. So just looking at this problem here, I don't really see anything that is going to cause an angular impulse, right? There's no moment that's being applied for a certain amount of time or anything like that. All we have is this cord and then the little mass that's going around in the circle. Okay, so because of that, this can go away, and then I'm left with just this side, which then has to be equal to 0. So let's go ahead and write all that out. So that left side goes to 0. So then the change in the angular momentum is going to be 0. All right, which then means that the angular momentum at time 2 is going to equal angular momentum at time 1. Okay, and I'm going to go ahead and use the scalar formation for angular momentum. So remember, angular momentum is basically the moment of linear momentum about our axis of rotation. So if we look here, I am rotating about this vertical line, right? So I'm going to use the scalar formation, which is going to be m times v, that's the linear momentum, times d. Now this is going to be for our second time, which will be right here on path B, right? So let's put a little subscript here. So mvb db, and then that's got to equal the angular momentum that we have on path A. So we're going to have m, because that doesn't change, times VA times DA. All right, so now I just need to plug in these values. So let's come over here and do that. The mass, that's not going to change. That's 2 kilograms. So we're going to have 2 kilograms. We're going to multiply it by the velocity at B. Do we know that? We don't know that, right? That's what we're looking for. Because if we look right here, it wants the speed of the bob around path B. So that's an unknown. We're just going to leave it as VB. And then I need DB. Remember, that is like a moment arm, right? So I need to have a distance from my mass, which is here, to the axis of rotation, which would be right here. And it needs to be perpendicular, just like with a moment. All right, so with that, I need this distance here. Notice this right here for B is 300 millimeters. So that means what we're going to have is 0.3, if we put it in meters, sine theta B. And that theta B, that is going to be this angle right here. Right? So it's the angle between that vertical line and the cord when it's holding the mass in path B, right? Because remember, we got to have like a moment arm. It's got to be perpendicular. So that will give us this perpendicular distance right there. Okay, so that's going to be our left side. We do the same thing for path A. Let's see what we get there. Mass is still going to be the 2 kilograms because that's not changing. Velocity, do I know the velocity here? I do. That was 1.5 meters per second. So we're going to have 1.5 meters per second here. And then I need D. So again, I want the moment arm. I'm rotating about this axis. So I want this distance right here. That's going to be perpendicular. So this length is 600 millimeters. Let's convert it to meters. So it's 0.6. And then I'm going to have a new angle that goes from here to here. Let's call it theta A. And we'll use purple, I guess, for that one. So this is going to be theta A right there. So with that, we're going to end up having 0.6 meters times sine theta A. All right, so now we've got those. We can go through, simplify. This left side will be 0.6 VB sine theta B. And then the right side is going to be 1.8 sine theta A. All right. So now we've got that. They're set equal to each other. Let's call this equation 1. Let me use a different color here so we can easily find it in a minute. All right, so there's equation 1. Now notice what that gives us. It gives us a relationship between the theta value at A and at B. So it allows us to relate those two things together, and we're going to need that in just a little bit. Now that's all I can really get from angular momentum here. All right, so we know we have conservation of angular momentum, but I don't have a way to find that velocity at B because I have too many unknowns in that equation, right? There's 3 unknowns. I've got this one equation. So that means I have to find another way to go about getting one of these unknowns. All right, so the next easiest thing to do, if we look at this problem, we know we've got a mass, I've got forces here, right, because I've got like the tension, we've got a weight. So let's look at kinetics. All right, we're going to look at kinetics in the normal tangential frame. Let's see what that gives us. First thing I want to do, let me scroll back up here. Let's draw our free body diagram. Let's do that first. And then we can go from there. So let's put it over here. So here's this little mass. And if we look on here, we kind of already talked about it, but there's our mass. I've got this cord that's going to provide a tension going up in that direction. So let's put that on here. If y'all hear background noise, it is because somebody is mowing the yard outside across the street from me. Now, besides tension, we've got the weight, right? So that's going to be mg. Now let's kind of draw a frame on here. So first let's do a vertical axis right here. And let's just call it z. And then I need the normal tangential frame. So the normal direction, remember, is going to go in towards the center of curvature, and then when we are rotating, we're going to have that tangential direction. So that's going to be tangent to the path like that. So if we put that on here, we're basically going to have a T and then an N, right? Something that looks like that. And this angle right here, let's call that theta, right? Because that's going to match, you know, our theta right here. Now that'll be our free body diagram. Now let's go ahead and look at our equations. So notice this is kind of like a 3-dimensional representation, right? So the axes that we're going to want to evaluate will be the z direction and then the n direction, because the tension here is basically in that nz plane. So let's go ahead and look at those equations and see what that gives us. Let's go ahead and start with the z direction here. All right, so we're going to say up is positive. We're looking in that z direction. That means we're going to have a component of tension going up. So that'll be t cosine theta, and then we're going to have minus mg. All right, so t cosine theta minus mg. And what do we think that's going to equal to? Do I have an acceleration in the z direction? No, right? So that'll be 0. And we know that because it says it's in the horizontal plane. So all of the motions in that horizontal plane, there's no upward or downward motion, okay, when we're rotating in path A, for instance. So that gives us this. We can go through, plug in m times g, because m is, what is m? 2 kilograms. All right, so we're going to have t cosine theta equals 2 times 9.81. We can then divide by cosine theta and get t. So t will be 19.62 over cosine theta. And let's call this equation 2. Let's go ahead and look at the normal direction now. Now the normal direction is this way. So the only force I have in that direction is going to be this t component, right? So that's going to be t sine theta. It's going to be in the positive direction. So let's kind of look at that. All right, so we have t sine theta. That's the only force. That's got to be equal to the mass times the normal acceleration. The normal acceleration, remember, is v squared over rho. Okay, so we're going to have m and then v squared over rho. So let's kind of fill in some of that information. Let's leave the left side alone. I don't have anything to change there for now. And then on the right side, we've got a mass of 2. And then let's make this as generic as possible, right? And I want to do that because I've got the 2 different paths, right? I've got A and then I've got B. So we're going to have different velocities here. I'm going to have a different radius of curvature for each one of these. So let's make it generic, and we're just going to leave this as v squared. Now rho is going to be, you know, this distance here or here. In both cases, it'll be this length of the chord times sine of the angle theta, right? So let's just have v squared over, let's call it L sine theta, right? And that way we can use it for path A or for path B. And let's call this equation 3. Okay, so now I've got that. Let's go ahead and look at our equations. I've got t in both of these. So let's go ahead, let's plug equation 2 in right here and see what we can get with that. So let's plug equation 2 into here. Okay, I don't know why it made a square, but it did. And if we do that, we get 19.62 sine theta over cosine theta. And then we're going to set that equal to, you know, we have the 2v squared over L sine theta. Now we've got that. Let's get all of our theta terms together. So let's cross multiply. Let's take the sine theta and multiply it over here. We can leave L down here for now. And then if we do that, we're going to end up with 19.62 sine theta squared over cosine theta. And then that is going to be equal to 2v squared over L. All right. So now we've got that. I've got sine squared over cosine. We need to do something to simplify that because obviously I can't just put that in the calculator to solve for theta, so we need to simplify it somehow. So let's go ahead and we can replace that sine squared with 1 minus cosine squared theta. That's a 2 there. So let's replace that, put it in here. And then we get 19.62 times 1 minus cosine squared theta over cosine theta, and then that's going to equal 2 times v squared over L. Now, essentially what we need to do is kind of get rid of some of these values so I can solve for an angle. Now, if we look back at what we're given for path A, I have the velocity, it's 1.5. I also know the length, L, right, 600 millimeters. So I can get my angle theta A using that velocity and then that length. So let's go ahead and plug those values in for path A and see what we get for theta. All right, so for path A, our velocity is 1.5, and the length, if we put it in meters, is 0.6. So we're going to go ahead and put those in. And then this will give us theta A, right? So I'm going to switch over from theta, and I'm going to call it theta A now. All right, so we got 2 times 1.5 squared over 0.6. And then last thing you have to do is kind of do some algebra. We're going to get a quadratic equation that we can solve, and then that'll give us our theta A. All right, so if you go through, kind of cross multiply and then group all of your like terms, then what we're going to end up with is cosine squared of theta A plus 0.3823. Oops, let me rewrite that. Cosine theta A and then minus 1 equal to 0. Now when you solve that with the quadratic equation, you get two values, right? You're going to get cosine theta A equals negative 1.21, and then you get 0.827 roughly. Now if you go ahead and try to do the arc cosine, this one here is not going to work, so we're going to want to use the 0.827. Alright, so we're going to have theta A is equal to the arc cosine of 0.827, which is equal to 34.21 degrees. So now I've got my theta A. Alright, now if I look back up in my equation right here, equation 1, I have a relationship between theta A and theta B, and it also has VB in here. So now I got to somehow figure out how to get theta B. All right, now can you think about how we could do that? Well, first thing I'm going to look at is the fact that I know what theta A is. So theta A we already found to be 34.21, so that means I could plug that value in here, and then we have VB and still theta B are unknown. But let's go ahead and do that and see what we can get with that. So this is going to be from equation 1. Let's make that look better. All right, so there's equation 1 here. So with that, we're going to plug in that theta A value. So we have 0.6 VB sine theta B. That's going to be 1.8 times sine of 34.21. Now let's see what that equals. Well, that gives us that VB sine theta B is 1.69. So that's after we calculate this right-hand side, divide by 0.6. This is the relationship we get. So I've still got two unknowns in this equation, right? Now, we're stuck with this. But I've got this equation here. This also has velocity and an angle, right? So we wrote this here to be pretty generic, so we could use it for either path, so A or B. Now we want to find the information for path B. So let's go ahead, let's look at equation 3 here. Let's solve this equation down here for VB, and we'll plug it in and see what happens there. So if we do this, VB will be 1.6, not sure what kind of 6 that was, 1.69 over sine theta B. And let's take that, plug it into equation 3. This problem is a lot longer than I anticipated. So if we do this and plug this in to equation 3, what we're going to end up with is T sine theta B, and then that's going to equal 2. Now we have V squared, right? So I need VB squared, so that's 1.69 over sine theta B. Let's square that. and then we're going to divide it by L sine theta. Now L for path B is a different value, right? That's going to be the 300 right there. So we're going to have 0.3 meters. So let's put 0.3 meters here. And then we need it to be times sine theta B. Okay, so now we've got this huge mess to mess with. So let's go ahead and let's simplify it. So we're going to have a sine squared on the top divided by sine on the bottom. So that's going to give me sine cubed. I'm going to move those both to the left side. And let's calculate the remaining value here on the right. That gives us t sine theta b equals 19.04. And again, I'm going to move those sine terms over, so we end up getting sine to the 4th on the left side. Okay. Now I've got t, I've got theta b in here. I don't even want those two unknowns. I know from up here, equation 2, we've got this tension equation that just has theta in it. So let's take this, let's plug it in for t right here and see what we get there. All right, so 19.62 times sine to the 4th theta b over cosine theta b, and then that's the 19.04. So still not really much we can simplify. We can move the 19.62 over to the other side, divide there. That'll give us 0.970. So then we're left with that left side. So we've got sine to the 4th over cosine. So basically we could rewrite that as sine cubed times tangent of that theta equals the 0.9704, right? Now you're just kind of left with that. You can't really simplify that anymore, right? This is one of those fun problems the textbooks like to throw out there sometimes. So best thing you can do, let's move the 0.9704 over, and then you're going to have to use your calculator, MATLAB, something to solve, right? Your textbook or the Hibbeler books likes to call it trial and error, right? So basically they assume you're just going to sit there and plug in numbers repeatedly to get the right value. But you could put this in MATLAB or something like that, or your calculator probably, and solve for theta. And the value that we come up with when we do that is going to be that theta b is 57.866. All right. Okay, so that is what we get there. Now, I would assume you would not get a problem like this on a test, right? I didn't really anticipate this part of it when I started working it out. Now we got that. We still got to find our velocity, but that's going to be easy now, because if we scroll back up here, we've got this relationship, right? I know theta A, I know theta B now. That'll give me VB. So let's go ahead and find that. Actually, there's this shortened version right here. So we can say VB is 1.69 over sine 57.866. Let's see what that gives. Gives us a value of 1.996. And that'll be meters per second. So finally, after all of that, we get the velocity on path B. That was a lot of work, wasn't it? Okay. And remember this solution up here, this is from like a computer. All right. Because you can't really calculate that very easily by hand. Now, last thing it wants us to do is the work done by the force, right? So that's going to turn into a work energy type problem. So let's look at that. So remember, work is going to be essentially delta T plus delta VG plus delta VE. We don't have anything elastic, so this term here is going to go to 0. That leaves us with our kinetic energy and our gravitational term. So let's go ahead and fill those in, and then we'll look at the work for the force at the end. Okay, so delta T is going to be 1/2 times the mass times VB squared minus VA squared. So it's 1/2 times 2. VB was 1.996, square that. VA was 1.5, so square that. And that gives us 1.734. All right, so we've got that. And then I need delta VG. Now remember, when we're doing this, we're going to do the weight times the difference in the heights, right? So we got to come up with a reference point to measure all of these things from. So if we look back up here, I think this point right here would be the best choice, right? Because we can measure easily from that point. So let's make that top point our reference point. And remember, the H value is a vertical distance, okay? If we're below the reference point, it's going to be a negative value. So at point A, I am down here. So I need this distance, which is going to be 600 millimeters times cosine theta, right? And I'm going to switch it to just meters. So we'll have 0.6 times cosine theta for A. And then for B, likewise, we would have the length of the chord times cosine of theta. So that's going to be 0.3 times cosine theta B. Whoops, wrong color there. So this will be mg times 0.3 cosine theta B, and then we have a minus 0.6 cosine theta A. Remember, I said it would be negative if we're below the reference line, so put those as negative there. And let's see what we get. Remember, 2 is the mass. Okay, so we're going to have 2 times 9.81, and then times what's in the parentheses here, and this one becomes a positive. All right, and we have our thetas, right? Theta B was 57.866, and theta A was 34.21. Let's calculate that one. So that is going to give us 6.604. Units here would be joules, by the way. And then last thing we need to do, since I've got everything on the right side, I need to look at U. Now remember, in order to have work done by a force, you have to have a force and a displacement in that same exact direction of the force, which we do have that there in this case, right? Because we have a force in a vertical direction, and then the masses are moving in a vertical direction. Okay, so there is definitely work there. So let's call this U sub F, and then that is going to be 1.734, and then plus 6.604. So now what does that equal when we add that up? Let's see, that is 8.34. All right, so we got 8.34, and that's joules or Newton meters, whatever units you want to use there. But that'll be our work due to the force. Now, y'all, that was a long problem. Okay, had no idea it was going to be that long. But there we have it. At least we got it done, right? Okay, so hopefully that kind of shows you how you can combine kinetics, angular momentum, work energy. You can combine all of those topics together into one very, very long problem. All right, but hopefully you found it helpful. So I wasn't really expecting the computer or MATLAB solution to be required there on that one, but it is what it is. Okay, hopefully you like that one. I'll see y'all again next time for hopefully a slightly shorter problem. Y'all have a good day.